Hey everybody, this is Alex Merced, and here in the first lesson what we want to talk about is what is the problem that existed that Apache Iceberg is solving. So what is the problem and what is the solution? To put it kind of everything in the context, like why are we here, why do we care, all that fun stuff. So it all begins with understanding sort of what is a table format to begin with, because at the end of the day, Apache Iceberg is a table format. So we need to understand like what is a table format for. And basically, the way to think about it is that when you're using something like a database or a data warehouse, tables, the whole idea of a table is something we take for granted. We put data in a database and we have no idea how under the hood that database is organizing the data, optimizing the data, accessing that data. All we know is that, hey, I can run a SQL query on a table and it executes. Same thing in a data warehouse. But what happens when you're operating on a data lake? So now let's say that you now have all your data spread across many files in a data lake, which in this case we'll say is object storage on your favorite cloud provider, whether that be AWS, Azure, Google Cloud, and so forth. You have, let's say, thousands, if not hundreds of thousands of Parquet files, and they all represent different data sets. But it's not just one data set per file. You might have 1,000 files that represent one particular set of data. Another maybe 10,000 Parquet files over here that represent one set of data. So how am I supposed to use different analytical tools and be able to know, okay, these files are one data set, one table, and that is the purpose of a table format. The idea is to be able to recognize groups of files and be able to recognize those groups of files as a singular data set, a singular thing that I can then run analytical operations on. Okay? And to kind of go further back on like why this problem had to be solved is back in the early days of data lakes, you would use something called MapReduce with your Hadoop cluster. And what would happen is that MapReduce required you to write these sort of complex Java scripts that would say, okay, hey, let me go say these files are my data set and then run these operations on them. So everyone had to kind of decide which files were they operating on, and people would do it inconsistently, and it wasn't great. So what they did is that someone created Hive, okay? And what Hive did, which originated out of Facebook, is that it said, okay, to make life easier for people, instead of having to write these complex JavaScripts, we'll let you just write SQL. And what Hive's going to do is just take those SQL statements, those SQL jobs, and translate them into a MapReduce script. But in order to do that, we need to have a way of recognizing tables. Okay, so essentially Hive had to figure out, okay, how we're going to be able to like represent things as tables, so that way we can actually use things like SQL, and then to extend that even further, be able to just recognize tables in any kind of tooling. So the approach that Hive took was a directory-based approach, where it would just take and say, hey, this folder, this directory of files on your Hadoop cluster, okay, is a table. Okay, and that works. Basically, we know that if a file is in this folder, it's a table. And that's basically if I say, hey, I want to select all on table 1, it's going to look inside the table 1 folder, and any files in there are part of table 1. And if there's any subfolders, those would be the partitions, and so forth and so forth. So this worked. Again, all based on folders. So essentially what would happen is that the engine would know that's the folder with the table. I'll go in there, I'll list all the files in that directory, list all the files in those subdirectories, and then that's the data I'm going to scan. Now there was some very big benefits to this becoming sort of like the industry standard, because Hive took over things by storm. This ability to be able to like just treat the data in your data lake the same way you would treat your data in a database or a data warehouse, to recognize those groups of data as tables. And this became the de facto standard. And the beauty of that is that it was compatible with everything. You could use any tool that you want, and so forth. And on top of it, like, you're able to actually have more efficient patterns doing this, because instead of like, you could organize your data through partitioning, where you can sit there and say, okay, this subfolder has all the data for the month of June, and so forth. You could do it by date, by any particular like column or field. And basically what could happen is if I run the right query and say, hey, give me all the data that is on this month and that year, instead of scanning all the files, which would take much longer, it'll only scan the files in the proper partitions. So I'm able to speed up my queries because of these more efficient access patterns, aka partitioning. It's file format agnostic. Okay, again, if the file's in the directory, it's part of the table, whether it's a CSV file, a JSON file, a Parquet file, whatever file, ORC files, whatever you want. Okay, it is able to atomically update a whole partition. So if I wanted to update the data for July 2021, I can update that atomically. Okay, so that will be updated, and I don't have to worry about I get all my fun asset guarantees. Okay. And again, it provided a single answer to what is a table. So essentially, you don't have 10 people writing 10 different MapReduce scripts and coming up with 10 different versions of the same data set because they didn't include a file or included extra files. You had the table, and no matter who ran what type of analytics on that table, they were running analytics on the same data set. And there's a lot that could be said for that. Cons. Smaller updates are very efficient. Again, everything's very directory based. So what happens if you only want to update one record that's in one file in one partition? Hive didn't really have a good way to handle this. Okay, so essentially what you'd have to do is update the whole partition, because it's going to have to go in there and say, okay, I'm going to go update this partition. Let me go look at all the files, find the record you want to update, and then rewrite the partition. Not the most efficient pattern. So small changes were very inefficient and very time consuming. There was no way to change data in multiple partitions safely. So if you wanted to change like multiple partitions, you do run the risk that, hey, after one partition's changed, okay, and it begins work on the second partition, that someone comes in and queries the data in the middle of that update. Okay, and that would not necessarily be the best thing in the world. In practice, multiple jobs modifying the same data set may not be done safely, okay, because you have different people trying to update the data at the same time, and there wasn't really good mechanisms in just that base Hive format to make sure you can get those asset guarantees. And then, since it was directory based, what would happen is that you would have to constantly start out by going inside the folder, getting a list of all the directories and list of all the files, and then go inside those subdirectories and get a list of all those files. And these operations took a long time. And sometimes being able to filter out files required you to read those files. So all this opening a file, reading a file, closing a file, then opening the next file, then reading the file, then closing the file, made things more time intensive. Okay, essentially there's really going to be two ways you can speed up a query. You can either do more quicker, meaning more processing power, but more processing power, more compute, generally it's going to mean bigger price tag because you're procuring more compute power from your favorite cloud provider, whether it means more clusters or more powerful instances on those clusters. Or what you can do is you can try to end up doing less work to get the same job done. Okay, and this is why we do things like partitioning and indexing and materializing and all these kinds of things, because they allow us to do less work to get to the same result, which also, even better, reduces our costs because we're not having to pay for more compute power. Okay, so the problem is doing all these file operations made things more inefficient, again, meaning you're going to take more compute to get the same job done, more expensive, versus not needing that compute. Okay, and users have to know the physical layout of the table. So again, there's partitioning. So again, partitioning, what we do is we take the full data set and we break it up into all these like sub data sets. So here's the data for June, here's the data for July, here's the data for August, and they're all broken up into subfolders. But oftentimes you can't just say, hey, where's the data? Here's the data for August, because typically that's not what the raw data had. The raw data generally has like a timestamp. So there might be a timestamp for when an order, assuming this is sales data, was taken. And the problem is that I want to partition it by month and year. I don't need to partition every individual second or millisecond. So what you'd have to do is you'd have to create some derived column. So you'd have to create a column that takes that timestamp and generates like a number for which month it is. Take that timestamp column and generate what year it is in a separate column, and then partition the table based on those columns. So you'd have like a year and a month column, which your data consumers may not necessarily be upfront aware of. So then basically, for you to benefit the partitioning, you would actually have to, when you run your query saying, hey, give me all data between this timestamp and that timestamp is not enough. You'd have to add additional filters filtering on that month and year column to get the benefit of partitioning. So basically, people who are querying the table, your data consumers, would actually have to understand how the table was engineered. Because if they didn't, they're going to accidentally forget to put those additional filters on, and they're going to end up with a full table scan, which is going to take forever. So you could easily get these accidental tables, full table scans, which are really slow, very costly, and that's a downside. Like we want to make that easier. So avoid this whole situation where people need to understand intimately how this table is constructed. And then basically, if you want to get Hive table statistics, you'd have to run these analyze queries periodically. Okay, and every time you run these analyze queries, essentially what would have to happen is that you do this job where you have to read every file, read the entire table to generate these statistics that you can then compare against the previous time you ran those. So generally, like the stats you had on your table were only as fresh as often as you ran these analyze jobs. That's not necessarily very great either. And again, having to spend all that compute, having to recalculate all the stats every time you did it. So how can we resolve these issues? Obviously, like we might need a new paradigm. So this is why we needed like a new table format. Okay, and particularly at Netflix, several different like issues were needing to be resolved, and so there was several goals that Netflix wanted to achieve in creating a new table format. Okay, including wanting to make sure that the table is correct, consistent. Again, the idea that having a consistent definition of the table, so that way everyone's doing operations on the same data. Faster query planning and execution. Okay, if I don't have to like generate a list of all the files at the beginning of every query, I can save some time. There's better ways for me to figure out, hey, what are the exact files I have to scan? Again, do less work to get the same result. That's going to end up having a faster query, but also a more inexpensive query, because again, if you generate performance by being more efficient, you're saving time and you're saving money, versus just more compute power where you're saving time but not saving money. Okay, we want to allow users to just be able to query the data and not have to worry about the physical layout. They don't need to think that there's this month and year column. Okay, they should be able to just query the data based on the timestamp field that was originally there and still get the benefits of partitioning. Tables evolve. Your data is going to change, your data is going to evolve, and your needs are going to change. So being able to like change the schema of your data, change how you partition the data, giving the ability for your table to be able to like evolve over time, also very valuable. And the ability to accomplish all of these at scale. And then that's kind of where we end up with Iceberg, which is essentially takes this different approach where a table is a canonical list of files. Okay, a canonical list of files. So essentially, instead of saying, hey, the table is all the files in this folder, theoretically, an Iceberg table could be anywhere. The files can be in different folders, and it doesn't have to be in some sort of nicely organized directory system. Because what's going to happen is that Iceberg is going to have the list of files in its metadata. And the engine, instead of having to go like look through each file to see what each file wants, it's just going to look at these lists of files, these manifests, and be like, okay, these are the files I need. And then do the scanning. Okay, and that's going to allow us to do things faster and better. Okay, so at the end of the day, what is Iceberg and what isn't it? Okay, at the end of the day, Iceberg is a table format specification, meaning it's a standard. Okay, so essentially it's a standard for how do you organize the data around the table. So as you'll see when we do talk about the architecture, we break up that data into sort of like 3 tiers. And basically any engine that wants to write an Iceberg table, any engine that needs to read an Iceberg table will have this open specification so they know exactly, okay, when I want to read this table, where's the data that I'm looking for? If I need to write to the table, how do I organize that data so that way everyone's playing from the same rulebook? And since everyone's playing from the same rulebook, more tools are going to be able to use it, and that's sort of like that openness is the big benefit. But in making that easier for more engines and tools to be able to implement Apache Iceberg, there are several sets of APIs, Java and a Python API, and several other libraries that make it easier for one to use um, Apache Iceberg with open source tools. So the Apache Iceberg project actually creates the implementations of Apache Iceberg in tools like Flink and Apache Spark and so forth. And then other engines can then use like the Java and the Python APIs to help underpin their own implementations of the Apache Iceberg format and use a specification to figure out how to write their own custom readers and writers that work with their particular tooling. Okay. Now, what Iceberg isn't is a storage engine. Okay, you do not store your data in Iceberg. You store your data in your data lake, in your data lake house. Okay, whether that typically is probably going to be object storage, but it doesn't have to be. Okay, and that's one of the beautiful things about Iceberg, that it's because it kind of breaks itself away from that Hive file format. It works really well on Hadoop storage, basically HDFS, the Hadoop file system, and it works really well on object storage and avoids the, it's designed that's flexible enough that it could just different implementations, so that way you avoid the bottlenecks in each particular platform and use it the way that it would work best on the particular storage layer you're using. It's not an execution engine. Okay, so while the Apache Iceberg project does create implementations for how open source projects like Apache Spark and Apache Flink will read and write to Iceberg tables, any other engine that's going to like read and write to Iceberg would come up with their own readers and writers and tooling to get that job done. So you're going to get sort of the way different engines are going to treat Apache Iceberg tables are going to be very different to that sort of engine's needs and goals. It's not a service, okay? So it's not something that you just run. So you don't have to set up like an Iceberg server, okay? Which is great because now you don't have to go set up another thing that's just running all the time somewhere. Iceberg is just a specification. It's just sort of a standard of how you lay out the metadata files and how engines can read those metadata files to relate to that data. Okay, so you don't have to worry about like this other process that comes along with you running Apache Iceberg. It's just the standard, so that way everyone's playing from sort of the same rulebook when it comes to accessing your data on data lake storage. So this ends up bringing a whole bunch of benefits to the table. Okay, you can efficiently make smaller updates because you don't have to go look through every folder and file and update a whole directory or a whole partition. You can update the one file with that one record you're looking to update, and that's the only thing that's going to get updated. And then you can even not even necessarily have to update the file or rewrite the file. You can actually sometimes just track, hey, this is the thing I'm deleting. So you can make it really, really efficient to make really, really small updates when needed, okay? Because you're making changes at the file level, not the directory level. You have snapshot isolation. So essentially, anytime the table changes, when it's created, when it's updated, when records are deleted, a snapshot is created, okay? And because of that, all reads are always on the newest snapshot, and writes are always creating a snapshot. There's never going to be sort of like this rolling over each other. Okay, a read is not going to read a partial snapshot because there is no such thing as a partial snapshot. You either wrote it or you didn't. Okay, and multiple writes, well, they have to check that their new snapshot is in sequence, so that way they don't trip over each other either. Okay, that's how we end up getting concurrent writes. You get faster planning and execution because again, you have all this data that allows you to determine what files are part of the table, along with a lot of metadata on those files, as far as like what data is stored in those files, how much data is stored in those files, that engines can use to more effectively plan their queries. Okay, so you have a list of files. That list of files gets defined on the right side, and the read can then use that list that was created to help plan the query more efficiently. Okay, column stats are also generated during the write side. So when you write queries and it's updating all these metadata files, all these stats are being generated in those files, and then again makes it much easier to generate column stats. Like you're not having to read the whole entire table every time you want to update your statistics. Okay, because again they're being updated every time you write. Now you're abstracting the physical and exposing a logical view. So again, the idea being that people don't have to care how these files are organized under the hood. Okay, so again, the files don't have to be in any particular place. The files, basically, long as the Apache Iceberg metadata knows where these files are and understands they're all part of the same table, someone running a query just runs a query, and the engine will do the rest of the work. So they just have to think about the logic of this being a data set. That there's this table called table one, and I can run queries on it. Okay, I don't have to worry about the partitioning because there's this feature called hidden partitioning that makes it where if I query that timestamp field, it works. Okay, even if I'm partitioning it by month, year, day, so forth. Basically, you're going to be able to run compactions because the Apache Iceberg API gives you tools to make it really easy to run compaction, which is a thing you do to optimize your table. Because if you're streaming in data, you're going to generate a lot of small files, which can affect the speed of your queries. So by running a process which takes those small files and turns them into bigger files, you're going to have better performance. And Iceberg kind of gives you, packages this in its procedures right out of the box. Tables can evolve over time. Okay, but not only can you evolve the schema of the table, something very unique to Iceberg is that you can evolve the partition of the table. And because you have this ability to evolve and you have the snapshot, so you can actually roll back the previous snapshots if you make a mistake, data engineers can transparently experiment with the table layout. They don't have to worry about, hey, if they make a mistake, oops, I broke it. And that gives you, now you have that rich schema evolution support where you can change everything from the name of a column, the type of a column, you can drop a column, add a column, you can update the schema. And the cool thing is at the end of the day, any engine coming in to do a read is always going to read from the newest snapshot. So, you could have made an update in Spark and a query comes in from Dremio, and that Dremio engine is going to see that new snapshot right away. So it allows all tools to kind of work together because they're all playing again from that same playbook, which is the Apache Iceberg specification. Now, Apache Iceberg, again, is the key to unlocking data in the data lake, mainly because there's so many, the ecosystem that's created. Okay, people can create like a table format and you can have your data, but again, the table format needs people to use it. Okay, the benefit is the network effect, the fact that different things you can plug into. So if we take a look at the Iceberg project, you can see that the stars of the Iceberg project have accelerated a lot in more recent times. So I'm recording this as like Q3 2022 for reference for anyone who's watching this after the fact. And basically you have all these companies who are contributing to the development of Iceberg, okay? And the beauty of all these like companies is one, that means they all use Iceberg. So you have this big community behind it. They use it, they service it. So that this is a project that has momentum. There's no one who's sort of like controlling it. Instead of it's a collaboration between many parties. Okay, and you end up with a broad ecosystem because you have a lot of tooling that works with Apache Iceberg table, so you don't get that lock-in that can occur when only one thing works with that tool with a particular way of storing your data or table format or something like that. So you can see there's lots of different tools that you can just plug right into your Iceberg data, giving you you can use the right tool for the right job when you need it. Okay, so I'll see you all in the next video. We're going to talk about Iceberg and the data lakehouse. So I'll see you then. Have a great one. Enjoy.